and I want to mention the concept of frequency. We just have one main example, which is exercise 7.4. Exercise 7.4, sort of at the bottom of page 50. Bottom of page 50. A developmental psychologist surveyed 15 single senior citizens living in private apartments. Each participant completed a questionnaire on the number of telephone conversations he or she had in the last day. Their answers were as follows: 5, 0, 2, 1, 1, and so on. What we want to do is just summarize this information with a table. And what is behind here is, let's say here, behind the scenes. There is a random variable x, which could represent the number of, I'm not sure why I'm writing sideways, phone conversations. I just felt like it. Then the possible values of x that we know of could be more, but we've only surveyed how many people? 2, 4, 5, 10, 15 people. Am I the only one getting 15 people? If we count how many people, there were 15, which is not a lot, right? And we saw that there is some variety in the number of phone conversations that could actually happen. But there could be something that we're not seeing. But at least the range of lowest number to highest number gives me some possible values of x. And they range from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Just because 6 is never there doesn't mean it's not possible. Once I have the lowest and the highest that occurred, everything in between I have to assume is possible. I just didn't get someone that had 6 conversations. Okay. So there could be more, but based on my little sample of people, I have no evidence to go any further. So behind the scenes, there is a random variable. The number of phone conversations people have in a day, in that situation at least. And there are, therefore, probabilities that are associated with these. But we don't know any of these probabilities. So just to note, we have no idea. We don't know the corresponding probabilities. So it's not possible for me right now to ask, what is the probability that someone makes 2 phone conversations in a day? I have no idea. I know it's possible out of other possibilities. So there is a probability behind the scenes. I don't know what it is. And I don't know what a formula could be to figure it out. I have very little information. But it might still be a relevant question to maybe help the people or adjust phone plans or whatever it could be. All we have is a sample of 15 outcomes. Things that actually happen. So the experiment is pick a random person, see how many phone conversations they had in a day. We did that 15 times and we got some numbers. So let's summarize what we have here. in table form, let's say. What is the best layout? I don't know why I wrote this sideways. Now it's just annoying me. Well, we just want to count all the possible values of x, how many times they occurred. So here there could be, let's say, values of x. That'll be 0, 1, 2, 3, all the way to 7, 4, 5, 6, and 7. And then I want to see how many times they occurred. So I call that the frequency. I'll just put it like that for short, frequency. So now we have to check. In our list of actual results, 0 occurred how many times? 3 times. 1 occurred 5 times. 2 occurred, I see only 1. We're at the bottom of page 50. 3 occurred twice. Please correct me if I am missing 1. 4, I see 2 of them. 5, I see only 1. There are no 6s. And 7 occurred once. Now I can do a little check here to add them up and make sure that these numbers add up to 15. 3 plus 5 is 8, 9, 11, 13, 15. Okay, so I probably considered them all. So I can have that little check just to see if something went missing, especially in a long list of numbers. It's easy to miss one. Is everyone happy with the concept of frequency? Frequency. Just how often it occurred. So on the right, I have the actual names for outcomes, in this case, number of phone conversations. On the right, it's how often they occurred. Then what I have, make a column here, is what we'll call the relative frequency, where all I'm going to do is say, take 0, not phone conversations, for example. 3 out of 15 is the proportion of times when I got that result. So this is going to be 3 out of 15. Next one's going to be 5 out of 15. So I'm just making little fractions. 2 out of 15, 2 out of 15, 1 out of 15, 0 out of 15, 1 out of 15. Relative frequency. Because I could, in another situation, I could have had 100 people. And the frequency might seem, oh, I got a lot of them. But relative to how many people I actually surveyed, it might not be that impressive. So the relative frequency puts it sort of into context and compares it to the total. That a frequency of 5 for one phone conversation, 5 might not seem a lot as a number, but relative to the 15 total, 5 is actually quite a lot. The relative frequency is a little bit more meaningful. And then I can convert these to percentages to make them even more presentable. So I'll say here relative frequency percentage. How do I take the relative frequency to a percentage? Multiplied by 100. All very basic, simple, straightforward calculations. So let's just take one decimal place, for example. 3 divided by 15. I know it's super exciting. 20% exactly? All right. I'll put the percentage sign there. 5 out of 15, that's a third, so 33.3%. 1 out of 15. How much? 6.7, let's say, just one decimal, whatever. 2 out of 15. I'm pausing so that you can actually do it. 13.3. 2 out of 15 again. 1 out of 15 we've already gotten, so those are easy. 0 is of course 0. And 1 out of 15 is again 6.7%. The percentages, again, it's a presentation preference. It's just easier and nicer for people to think about percentages than it is fractions. There's no other real purpose. So the last two columns are exactly the same. It's just how do I want to present it. If I add up those last two columns, what should I get? I should get 100%, 15 out of 15. So I can use that as a little check. 15 out of 15, 100%, to make sure all my calculations are correct. Maybe my finger slipped and this one I didn't calculate correctly. If it doesn't add up to 100%, it'll show something isn't right. All right. Any questions on any number in that table? The frequency table. Frequency table. Now, what's the point of this? Why do I have frequencies? The point is that if I have a complicated situation behind the scenes, like I don't know what kind of formula drives how many phone conversations people have. I have no idea how to actually find the probability that a person has 3 phone conversations. I can use my sample of 15 people to make an educated guess and say if my sample is a good representation of how these people use their phone, then the probability of having 3 phone conversations is approximately 13%. Because that's what I got in my sample. Now, of course, the more people I use in my sample, the more accurate it's going to get. The point is, we can use relative frequencies to approximate the actual probabilities. When the actual probabilities are a little difficult to find, and in some cases I have no idea. There is no mathematical formula or anything, it's just the situation I don't know. Statistics is really all about using a sample to approximate probabilities and make decisions based on that. Now, of course, 15 people, you might argue, doesn't necessarily give me a good approximation. Maybe 100 people, maybe 1,000 people. Sure, those would be better. More people, more accurate, for sure. More people, then my approximations will be more accurate, for sure. But I sometimes don't have the option. And my resources are limited. I sometimes just can't have a bigger sample. I do the best with what I have. So that's the use of relative frequency. We can graph this as well with that was a B. I could graph these as well, just like before, just like for the probability distributions. You remember we graphed it with little bars? I could do the exact same thing. I'm going to save time and not do that because I have 8 of them, so it's going to be a little bit tedious. I'm going to show it in a second. I can graph them with bars just the same way. So very rough, I'll have for 0, 1, 2, and so on all the way 7. I'll have a little bar that's medium height here. No, not that wide. Over there. Maybe the 1 bar will be a little higher, and the 2 bar is a little lower, and so on. Right? And then we call this, when it's the graph, the bar graph, corresponding to frequencies and not the actual distribution, we'll call it a histogram. Why? Who knows why? That's just a name. But it's just another name for the little bar graph corresponding to the frequencies. And that's an approximation, of course, as well, just a visual version of it. So when they ask for the histogram, it's just the bar graph of the relative frequencies instead of the actual distribution, which they do ask in detail in number 2, but I'm going to show other versions just to save time. Any questions on any of that? Hopefully not a complicated concept. Is everyone happy that the relative frequency approximates the actual probability? That's the key thing here. To emphasize that, we will have some interaction. All right, let me know when everyone has some dice. Now, while you are collecting your very colorful 6-sided dice, let's remember exercise 7.1. Do you remember exercise 7.1? Can you page back in your notes and look at the answer for exercise 7.1? And we defined our variable as the largest number that you see among the rows. Remember? I know the dice are super distracting. I know it's a lot of fun. There's colors and you're overwhelmed. Do you remember exercise 7.1? This is what the distribution looked like. It was 1 over 11, 3 over 11, remember? Now let's suppose this came from something that is much more complicated and we couldn't figure out those actual probabilities. We can run some experiments doing what they say over and over and over and seeing the frequencies. How often do I get a 1? How often do I get a 2, 3, 4, 5, 6? So what you are going to do is make a little table, 1, 2, 3, 4, 5, 6. And then you are going to roll the 2 dice and make a little tick every time you get whatever you get. If you roll a 4 and a 3, you put a tick under 4 because that's the largest number. So you're doing this experiment over and over, seeing every time what is the largest number that you get. Sometimes you're going to get a 1 as the largest number. Most of the time you might get a 6 as the largest number, just to see how many you get in each case.
8.
12.
Okay, good enough. So we see, let's suppose we did it right. And we see that 4, we just happened because of randomness. We didn't get 4 as many times as we now secretly know we theoretically should. Right? This is what it actually looks like. But if pretend we didn't know that, our repeated experiments are trying to approximate the actual probability. And you see the first ones were pretty good. Pretty good. Now, if we do more and more and more, then eventually it'll be a nice even step graph. But we can use these relative frequencies as approximations of the actual probabilities. But you see it's not perfect. The more you do, the better it'll get. and eventually the 4s will catch up to what they should be if we just do enough of them. But the point is the relative frequencies serve as approximations to the actual probabilities. Does everyone understand that? Now, we cheated in this case because we already know what the probabilities are. Let's pick one where we don't know what it is, and we wouldn't even be able to find it necessarily. This is exercise 7.6. I'm going to roll 3 20-sided dice, and I'm going to take note of the middle number. Picking something where I don't know what the answer is. I don't know what this looks like. I have no idea. Right? I'm going to use my frequencies to approximate it, but first I have to understand what gets a tick and when. Now, I have, of course, a lot of options, and 1 to 20 will be too much. Right? It's just going to be too much to take note of that. So I'm going to put them in little bins, little groups. When I get 1 to 5, that'll be one group. And I'll always have a check in that column, whether it's a 1 or a 3 or a 5 as the result. 6 to 10 will have its own little group. 11 to 15 will have its own group, and so on. Just to make it more manageable for me to get the numbers. Otherwise, it'll take forever. It's a compromise that we're going to make. So you're going to roll 3 dice. You're going to take note of the middle one. Whichever bin it falls in, that gets a check.
5,
2,
4,
6,
1. Oh, 10. 4.
Did I get you a 6?
4.
One's fast over there.
Because everyone does it. I'm gonna write it and I just.
All right.
No.
Let's go with that. So now we have an idea of what is likely to happen and what is not. Now, I did group them up, so the picture is a little unclear. Otherwise, it would have just been a mess. But you still get an idea that, oh, the middle 2 groups seem to be more likely. Now, if you actually peek behind the curtain, you'll see it's actually perfectly balanced, coming from a more detailed situation with a more complicated formula that you might not know or care about. The point still is that our relative frequencies, by repeating the experiment and gathering information and possible outcomes, we can get a fairly good approximation of the actual probabilities behind the scene. Relative frequency.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.